This is Surveying 1, Lecture 4, and in this lecture we are covering the topic of leveling. Taping and leveling kind of cover pretty much all the distance measurement that we're going to be talking about in this course, and that's the reason for touching on that topic now, because those are the first two kinds of activities you'll be doing in your field projects. So basically, leveling is a process for vertical distance measurement. And we often say that when we are measuring vertical distances, that we are talking about elevations. So whenever you hear the term elevations, you should realize that it involves a process for measuring vertical distances. Sometimes we talk about it as measuring differences in height. And there are many ways to do this in simple circumstances. So the most common would be a vertical measurement that you need to do, such as how high a table is off the floor. Well, you might be able to use a yardstick if it's less than 36 inches above the floor and simply measure that vertical distance. You might want to know what the height of the frame on this screen is. You could measure that directly. You could even measure buildings. You may have seen measuring poles, special measuring poles that are fiberglass, that are used to measure things like the height of a power line, because they need to move some equipment that's over height, perhaps down a road, and they'll use the measuring stick to figure out how high it really is to the underneath of the bridge, because the signs always have a little bit of factor of safety in them. They might measure to power lines and other overhead cables and so forth. These would all be what I refer to as direct measurement from one surface to another to get this height. So if you have a building, for example, and you need to measure the height of the building, if it's a relatively short building, you could do that with some kind of a measuring stick. You could even, if it's a taller building and you had a long enough tape, and you had clear line of sight, and you didn't have to worry about wind making the tape not lay flat against the side of the building, you could conceivably lay the tape flat against the building and measure it. People have been trying to do this for eons, since prehistoric times, by doing things like throwing objects off and seeing how long it takes them to get to the bottom, and calculating using the laws of acceleration and what's referred to as the terminal velocity because of the drag of the atmosphere on an object. There's all kinds of things that you can do. But there are some a little bit more sophisticated ways. The way that we will be concentrating on mostly in this class is called differential leveling. And it's probably the best process to determine elevations or differences in height between two or more objects that are not immediate to each other. So let's say you have, so here's the ground, and we have a building here. And we have a sewer. This is looking down the end of the sewer, and we need to get wastewater from here into the sewer. Well, one of the things that, and I'm exaggerating the scale here, there are certain standards for the minimum slope of this sewer line to be able to carry the waste away efficiently without any fear of it getting blocked up and all that kind of thing. So there might be a certain standard. And so one of the things as a surveyor you may need to do is figure out what is the elevation of the floor on the inside of the basement of this building, and what is the elevation on the invert of this pipe. And then you may not actually be able to see the pipe because they haven't started construction yet. And so when you look at this pipe extends underground. There might be a manhole over here that you can get to, where you can measure what's referred to as the invert elevation of the sewer pipe over there. And then coming out of the plane of the blackboard over here somewhere is another manhole, that way you can measure the invert of the sewer pipe down there. And let's say this is a sewer pipe that slopes downward. You're going down, dropping in elevation as you go from this manhole over here that's out of the plane of the blackboard to that one over there. So if you know the elevation of the invert there, and you know the elevation of the invert here, and you know the distance, the horizontal distance between those two manholes, you can now compute the slope of that line. And from that, knowing that where this line is going to come in from the house, you can figure out how many feet from this upstream manhole the house lateral, as it's often referred to, is going to intersect the sewer pipe. And so you can calculate that elevation. And once you know that elevation, and you know the elevation of the inside of the basement floor, the top of the basement floor, you can now measure the horizontal distance from there to where the pipe exists in the street to calculate what that slope is, to determine if you have enough slope to be able to properly sewer the building. So this would be an extremely difficult problem to solve if you only had direct measurement tools to use. So you have to use other ways of making these measurements. Well, what are some of these ways of making these measurements to get all this differential leveling done? Well, we'll talk about that, but first we need to cover some basic, very basic definitions. These things you should commit to memory. These are things that you should be able to recite without even having to think in this course, and if you stay in surveying as part of your career. We'll start with the definition of the vertical. The definition of the vertical is one of the most fundamental definitions in surveying, and it's very simple. It's the direction of gravity. Now here's the interesting thing. If you are standing 50 feet away from me, and you have the direction of gravity where you are, and I have the direction of gravity where I am, those two directions are not parallel. They actually all converge somewhere at the center of mass of the Earth. But there are many times when we assume that they're actually parallel to each other, and we'll talk about the subtle difference as we go on. The horizontal line or plane is exactly perpendicular to the vertical, which means to have the horizontal, to discuss a horizontal line or horizontal plane, we have to first talk about at which point on the Earth are we talking about. So if you look at the Earth, and we have this vertical, then the horizontal there would look like that. Whereas the horizontal over here would look like that. And they're not even close to being roughly parallel because we've gone an extreme distance away. The point is, even if you're 50 feet away, technically there's a very, very slight difference in the two horizontals. Now when we do what's so-called plane surveying, in terms of horizontal distance measurement, we assume that those two planes are the same. But in vertical distance measurement, we can't. We cannot. And the cool thing is, with the third method that I'll discuss, and even the second, these errors can somehow be compensated for, and we'll talk about where these errors come from. We won't go into it much in detail here. This course, it's mostly, this lecture, it's mostly descriptive. We'll get into some of the math later. Then we have a level line or surface. A level line or surface is basically, the simplest definition is to say it's a line or a surface of equal elevation. So it's a curved surface. So the surface, if this line I've drawn, this roughly circular shape I've drawn, is 0 elevation, then the 100-foot elevation would be something that looks like that. Turns out it's not so simple because the Earth is not a perfect sphere. It's not even a perfect anything. It's not a perfect ellipsoid, which is often the common shape that is used to approximate the shape of the Earth. Because what we are really dealing with is what's referred to as a gravimetric equipotential. It's where the strength of gravity is the same. It turns out because the mass of the Earth varies, that gravity actually undulates as you go out laterally. So it's not a nice even shape like this. Rather, and this will give you fits, rather it's going to look, I'm exaggerating of course, but it's going to look something like that. And if that's 100, 0 is not going to exactly be parallel to it. Because as you go on a vertical line, it turns out it actually varies. So it's going to be close, but it won't be exactly it, because there may be other impacts 100 feet down that cause it to be a little different from the one at the 100-foot level. And so this is where, when you get into doing especially GPS surveying, we'll talk about a concept known as the geoid. I'm just throwing this out for now here. Geoid basically relates to the gravimetric equipotential because GPS cannot determine elevations or differences in height using our system for determining what's up and down based on gravity. GPS does it a different way. And so the geoid, or what's called the geoid model, is used to convert from ellipsoidal height that GPS generates to give us something referred to as orthometric height or elevation. So this thing called elevation is simply height above what's called sea level. And in the old days, every country would have its own definition of sea level. I think the United States and Canada actually shared a common basis, and basically what they did was they took a whole bunch of stations along the Atlantic coast, the Gulf Coast, and the Pacific coast and measured sea level for 19 years and change. It's what's referred to as the metonic cycle. The metonic cycle is the cycle, the dance, if you will, in the heavens between the sun, the moon, and the earth. And that pattern of the metonic cycle only repeats 19 plus years apart. And so you have to measure sea level elevations for that period of time to figure out what the average is going to be. And so they averaged them at every station, and then they took all these stations along these coastlines where they were measuring the elevation of the sea to come up with some theoretical value. Now you probably know that sea level is not the same everywhere. So you can actually have the sea level in Maine higher or lower than the sea level in the Carolinas and higher or lower than the sea level at the tip of Florida in the Keys, which is in turn higher or lower than the sea level on the Pacific side somewhere. Those of you who know about the Panama Canal, you probably know that the Panama Canal has locks. And the reason it does is because the Pacific Ocean at the Isthmus of Panama is somewhere in the 40-foot level higher than the level of the Atlantic Ocean. So there would be these tremendous, tremendous rapids that would just rip the canal out if you didn't have locks. And of course the ships couldn't navigate under such kinds of currents. So they have to have the system of locks to enable them to navigate. And the only reason they knew this is by doing very careful leveling between the Atlantic side and the Pacific side. One of the few places on Earth where you can do that easily and get quite a high degree of accuracy because the distance is so short. So today, we very often say instead of elevation, this term orthometric height. So you should be aware of this because as you use GPS more and more, it becomes more and more important to understand what you're seeing here, which are really some geodetic concepts. And we've thought for many, many years as everyday surveyors that we didn't need to mess with this stuff. And that's no longer true. And that's one of the downsides of increasing technology. The so-called convenience is great for a lot of things, but you have to have a lot more knowledge base to be able to use it properly and actually deliver good results that someone else can depend on. Then we have the concept of datum, and datum can be anything. So you can be doing a project where somebody is building a shopping center, somebody's building a dam, whatever it is, and you can simply say, or you could be doing a sewer project for a small town of 10,000 people, and you can just say, I really don't care how high I am above sea level. I'm just going to set a benchmark here. And I'm going to say the benchmark is at elevation 1,000 or 100 or 250 or whatever. And then I'm going to very carefully differentially level to all the parts of town where we need to know the exact slope of the sewer or how deep the sewer needs to be under the surface of the earth, so that we can use gravity to bring all the sewage to that one common place, which is the sewage treatment plant. So this is a very common thing that's done. So datums can be arbitrary, or they can be, these are actually arbitrary as well, but somebody came up with a system. So NGVD 29, which is a United States vertical datum, stands for National Geodetic Vertical Datum of 29, is the one that was created by averaging all those station sea level elevations for that 19+ year period. The NAVD, which is North American Vertical Datum, and I'm fairly sure that's shared with Canada, of 88, they simply said, you know, what's the elevation using the old datum at this point? And they came up with a number, and they said, well, let's call it that here, and then we'll refer everything else to this one point and forget about trying to average sea levels. And whether you believe in sea level rise or not, or global warming or not, it doesn't really matter how it's being caused. You will know that if you do the research and you look at National Geodetic Survey or the National Ocean Survey, you will see that there's pretty conclusive evidence that sea levels are rising. They're not rising by much, but millimeters a year certainly are being detected. And these are very, very careful surveys where they actually are trying to bring out of the picture, when they look at sea level rise, they try to figure out, is this happening because the land is subsiding? Because there are some places where the land is subsiding for all kinds of reasons, including removal of oil and other liquids, fluids from the crust of the earth. You can also have sea level rise, and this happens in places where you're still having what's called glacial rebound. So as you know, we had glaciers over the surface of the earth for a very, very long time. This massive amount of ice caused the crust of the earth to get compressed. Now that the glaciers are melted, and even though it's been 10,000 years, they're still rebounding. And so you have some of that happening. You have things like tectonic plates clashing with each other, and that's what causes upthrust, that causes the mountains. And so you have issues where you may have to figure out how to deal with that. Are we having tectonic plate or crust raising that's happening, and it's not really dropping of sea level? So these are various things, and these are datums, and these are definitions or terms that may be new to you, and you should be committing an understanding of these to your memory. So here's a description of some of those things that I just pulled straight out of a book. So there's the vertical line, there's the horizontal line, and we have these the sea level datum. We have a corresponding level line, which is simply parallel to the sea level datum. And we have here the elevation of point A. And if the land looks like this, we can have points that are below sea level, above sea level, and so forth. And the way we do that is by constructing another level surface, so that by looking at the level surface through point X over here, and the level surface at point A over here, we get this vertical difference is the difference in elevation between point A and X. So you need to realize that when you find differences in elevation or vertical differences in height, you're actually finding differences in the vertical data, in the level surfaces that pass between the 2 points that you are comparing. As I mentioned, benchmarks are simply arbitrary representations of a reference surface, but you can have more of them because benchmarks are sometimes referred to as a realization of a datum. And so when we have things like this in the ground placed by the National Geodetic Survey, for example, they can be different types. And people think that these are all benchmarks, but actually they're not. This happens to be a horizontal control mark, so it may not even have an elevation that it references. This is a reference mark. It may also not have an elevation. But this is called a vertical control mark. And this would actually be a benchmark if it hasn't been disturbed and if NGS has actually done some maintenance on it, and there is a system for going to the National Geodetic Survey to figure out if the particular benchmark is a reliable benchmark that you can use. But keep in mind that if we have set benchmarks all over the country, that they've all been surveyed in very carefully, referring to that zero datum, wherever that zero datum happens to be, in either the NGVD or the NAVD, depending on what it is that the survey relates to. Keep in mind that we will have benchmarks that refer to older datums, and they should not be used today. So you always want to make sure that you check to see what the history is, what the documentation is on benchmarks. All right, so let's quickly talk about the types of leveling. The most common type of leveling that we briefly talked about even in the distance measuring part is this. And you simply have this situation. You want to determine the elevation of this point X down here, and you can measure down to it with your EDM, and this is simply a prism over here on top of this pole that you're sighting. You can measure this angle. So if you can measure this slope distance and you can measure this angle, then you can not only figure out what the horizontal distance is, you can also figure out what the vertical distance is to this point. And keep in mind, you're actually only determining the vertical distance from where the horizontal line intersects this vertical line down to the center of the prism. Then you have what's referred to as the height of your instrument above the point on the ground here, and then the height of the rod above the point here. They may not be the same. You can throw those into the equation and get the elevation of point X. So if you know that the elevation of, let's call this point A, is 100, and this thing is 5 feet above point A, the horizontal line of sight, then we know the elevation of this horizontal line of sight over here is 105. And if you calculate that this is 17 feet, and you know that your rod is 6 feet above the ground, then your total of 23 feet below 105 feet, and that gives you the ability to calculate the elevation of point X. So that's how trigonometric leveling works. So in barometric leveling, essentially we're using a barometer to determine heights or differences in elevation. And you may be aware that altimeters are actually barometers that are calibrated instead of showing atmospheric pressure, showing the elevation difference that the device has passed through. Now keep in mind, you could have a barometer simply sitting on a table and you could see it change in elevation as atmospheric pressure changes. So one of the problems with barometric leveling is that you always have to be aware of what barometric pressure is doing and making corrections for that. In fact, when people do extensive surveys using barometers, and that's not uncommon with geologists and people doing petroleum exploration and things like that, they'll actually have barometers in several locations around the project area that are recording barometers so that they can actually keep track of how barometric pressure is changing so that they can correct the roving field barometer elevations that are determined. So that's a fairly simple process, obviously not very accurate, They might have high resolution. They might even show elevations down to the nearest foot. But you're kidding yourself if you think they can really measure elevations that well. And then we have differential leveling. So differential leveling is basically this process. You set up an instrument known usually as a level, and you level it up such that you have a horizontal line of sight through the instrument. And you have a device called a rod, a level rod, and you observe, you have a point over here and a point over here. Let's say your eventual, what you need to do is determine the relationship between point A and point B. And so what you do is you you read where your horizontal crosshair intersects the rod, and you note that down. Let's say that's 5 feet. Now you do the same thing here, and let's say you now read 7 feet. Well, it doesn't take much looking at this to figure out that you now dropped in elevation 2 feet. So you're 2 feet below the elevation of point A. And the reason I selected that distance is because I can't go too far, because if I went all the way to point B, my rod might not be long enough, but there's other reasons for not going too far. So I set up again, and I repeat this process, and this time I read 4 feet and 7 feet, and the difference between these two is 3, so a total of 5 feet below point A. Point B is 5 feet below point A. So that's the basic process in differential leveling. And so the skills here are in setting up a stable instrument platform, being able to get the line of sight correctly horizontal, being able to read the crosshair, being able to read the rod. The rod graduations don't look like a yardstick, they're a little bit different. Being sure that the rod is not leaning forward or leaning back, causing an erroneous reading, because you want a rod that's truly vertical. And then this is more a mistake handling issue, but making sure that all your math is being done correctly so that you don't have any issues with your final result. Now, what's typical in a lot of situations is that if you're looking at this in plan view, it may be point A is here. This is your intermediate point here, so there's your intermediate point, and this is where point B is. So here's A and here's B. And what's very common in this kind of surveying is that you might then go to another intermediate point, so I'll call that intermediate point 1, here's intermediate point 2, and yet another one, intermediate point 3, and eventually close back to point A, because you should get, if you're calculating differences in elevation, you should get that point A is 0 feet difference in elevation from point A. And of course you won't get that, you'll get a slight discrepancy, and you have to figure out whether you have an error that you can handle or whether that's evidence of a mistake, and then you either decide to redo it or you decide to say, well, that's error that can't really be eliminated. So here's an older style level referred to as a dumpy level. So you have leveling screws. This thing attaches to a tripod, and there's a long bubble, so you can center up the level bubble. There's focusing for the telescope so that you can get the bubble in focus. You have a reticle that's mounted in there, and then you have focusing for the eyepiece so that you can get the crosshairs into focus. Today it's a lot more compact, and it's what's called an automatic level, so the work is much, much easier. Now you simply, there's a circular bubble over here. You simply put the level on a tripod, you turn the 3 leveling screws to get the circular bubble level, and then there's a mechanism inside the level that takes over and ensures that when you sight through the level, you have a horizontal line of sight. Now, later on, we'll talk about how all these things can go out of adjustment, and one of the techniques you'll be learning is how to make sure that your level is in good adjustment so that you're not delivering inaccurate results. Here's what the typical level rod looks like. And I'm going to leave it to you to read these graduations and try to figure out the method in the madness of the markings. I will say this, that when you have a point that looks like this, that it's usually 5/100ths of a foot. If it's on the bottom, between 2/10. So for example, let me use a different color. Over here, the bottom of that graduation, where here's 4 feet, so it's always 0 at the bottom, so 4.1, 4.2, 4.3, 4.4. So this would be that graduation where my arrow is pointing at the bottom edge of the mark would be 4.45. So the interesting thing about the way this rod is graduated is that the black bars are exactly 1/100th of a foot in width, but so is the spacing. So you actually read where your crosshair strikes the level rod at the bottom, and you measure off the bottom or the top of the black bars. So that's something you need to study and get familiar with. Here's a cutaway drawing of what it looks like inside the level. You basically have a couple of prisms and a mirror. Sometimes it's a prism. In this case there's a prism, sometimes it's just a mirror where the light bounces this way. And what happens is if the level is tilted one way or the other, these are suspension wires. And so this platform that holds the prism can swing a little bit this way and that. We're not talking about a whole lot, but probably a few minutes of travel in each direction. So you can have some error in how the level has been set up. That's very small. You couldn't do this unless it was on a tripod, and it will take over and correct the line of sight so that it is horizontal. This particular device is referred to as a digital level. And with a digital level, you, instead of the kind of rod I showed you in the earlier diagram, you have something that looks like a barcode. And so what this does is you still sight through the telescope to make sure that the field of view covered by the telescope includes the rod, but then you simply push a button and it takes its own readings and keeps track of your differences in elevation for you. This is yet a different kind of level used quite a bit in construction, sometimes used by surveyors as well, but there is a horizontal line that's emitted by this. Usually it's infrared, but it could be visible, and it spins. Sometimes this assembly here is actually called a lighthouse because it spins like a lighthouse, except we're talking about 10, 20, 30, 50 revolutions per second, or even faster sometimes. And so what you do is you hold your level rod, and if it's a visible light, you simply look at where the level, the horizontal line of sight strikes and wipes across the face of the rod. If it's invisible, or even if it's visible, there are detectors that they can make on a special rod that slide up and down, and either have a display that tells you when you're exactly on the line, or even an audio style of indication so that you can get there faster. And this is very convenient because now you only need one person. After you set up the instrument, you can walk anywhere within the field of view that this instrument can reach, and you can determine elevations very accurately with it. There's another advantage to this thing. If you have to put in things that have an incline to them, you can actually incline the sweep of that laser so that it's inclined down, maybe in this direction, and also inclined in this direction to do special kinds of surveying. And I want to conclude by just talking a little bit about orders of leveling. So when we talk about leveling, there are different levels of accuracy for leveling. The National Geodetic Survey sets some standards, but any organization can set its own standards. And National Geodetic Survey talks about first order leveling, second, third, and even fourth order, and sometimes there's second order, class 2, and so forth. They break it down for different purposes, for different applications. Just depends on what it is you're doing, where it's really critical for this purpose. And so generally, the leveling accuracy is expressed this way. Remember, I talked about going in that circle and closing back on your point of beginning. They all require a loop kind of leveling survey that's done. And that difference that you get when you come back to the point of beginning is called your error of closure. That's what EC stands for. And so you take the square root of the distance that you have traveled in horizontal distance in going from the beginning all the way back to the beginning. And you take the square root of that and somehow figure out what the relationship needs to be. And very often there is some kind of a constant that's applied over here. And so the National Geodetic Survey, for instance, will say, how many kilometers have you run? And there'll be some kind of a constant, I'll call it C, that's put in front here. So the square root of the distance multiplied by a certain number cannot, that the error of closure cannot, in millimeters, cannot exceed what the result on the right-hand side of the equation is. Finally, I just want to throw this out. This is more for you to think about rather than to try to fully understand. Be aware that when you have bubbles, that these are not cylinders. They actually have a curvature to them. Sometimes the tube has been bent a little bit, so it forms a circular arc. Sometimes it is a true cylinder, where the two sides are parallel to each other, but obviously you have glass on the inside, and the glass, instead of being exactly parallel to the outside, has actually been ground away like this. And that's what causes the bubble, and this is the bubble here. Let me just color it in blue. So that causes the bubble to rise to the top, because what the bubble is doing is actually responding to gravity. So when you level up a bubble tube, what you're really doing is placing the bubble tube such that its axis is perpendicular to the vertical. You want a 90-degree angle right there. So that's the basis for all surveying. You always are in a situation where you're trying to detect where the vertical is and then leveling up or adjusting the attitude of everything else based on detecting where that vertical line is and what its direction is. And with that, we will conclude this lecture.